Sample question number 17 here is, in a hydrogen atom, the excited color emitted due to the transition labeled by arrow D is. So the question is based on the diagram which has been shown. This is the diagram which representing the energy level diagram of the hydrogen atom. So as the energy, whenever the electron jumps from the lower energy level to the higher energy level, it gains the energy and it jumps to it. And whenever the electron jumps from the higher energy lower level to the lower energy level, it emits whatever the amount of energy it gained in the form of a light. That's what we say, in the form of a photon. Now question is about the energy level. What is the color of the light when it is emitted, which is shown by the arrow D? So with reference to this arrow D, I can say this is the higher energy level or the initial state of the electron. Let me represent as an Ni, and its value is gonna be 4. And this is representing the final state of an electron Nf, and its value is going to be 2. So by using the Rydberg's equation, this can also be called as an Barber-Rydberg's equation. We can calculate what is the wavelength of the light, and the wavelength of the light decide what is the color of the light. By referring to the wavelength and by referring to the spectrum, we can identify which wavelength has which particular color of light, and especially with the hydrogen atoms what we are talking about. Let's say, how do we calculate the wavelength of this light which has been representing over here? So let's see, as I mentioned, so we have to calculate the wavelength of the light by using the Rydberg or the Barber's-Rydberg's equation. So this is how the formula will be given to find the wavelength of the light. So 1 by lambda is equals to R H, that is 1 by nf square minus 1 by ni square. So as I said, lambda is the wavelength of the light with which is emitting. What is the wavelength of the emitted light? And the RH is the Rydberg's constant. That's the constant value, and its value will be given to you. That its value is going to be 1.097 into 10 to the power 7 per meter. And nf is the final state. As we said, nf is the final state and ni is the initial state. So that's what I have written here. Ni is the initial state and the nf is the final state. By using this one, let's first calculate what is the wavelength of the light. So I can make use of this expression as 1 by lambda is equals to RH value. We know that 1.097 into 10 to the power 7 in a bracket 1 by nf square, 1 by nf square. So what is the value of nf? As I said, nf here is going to be 2 and ni is going to be 4. So that's what we are making use of. So nf 1 by, so let me write it here, nf value here is going to be 2 and the ni value here is going to be 4 from the diagram which I am taking. 1 by nf square. So 1 by 2 square minus 1 by 4 square. So just substitute this value in the calculator. You're gonna get it as 1.097 into 10 to the power 7. So that's gonna be 1 by 4 minus 1 by 16. So with by substituting this value in the calculator, you will be getting the wavelength here as, so 1 by lambda. So 1 by lambda is equals to, you're gonna get it as 2 comma, so 2 comma 056 comma, it's gonna be 875. So this is the very big value what we are getting, 2 comma 056 comma 875. But actually we are looking for the wavelength lambda. So how do we, this is the value of 1 by lambda. So how do we get the value of lambda here? By reciprocating the flip. If you want to calculate the value of lambda, flip it. So flip both the equations. So then the lambda in terms of lambda can be written as lambda is equals to 1 by 2 comma 056 comma 875. So as this is a calculator question, if you put this values exactly, you're gonna get this as the answers. Okay, so that's 1 divided by this value of the lambda. We're gonna get here as, we're gonna get this value of the lambda here is gonna be 4.86 174 into 10 to the power negative 7 meter. So this is the value of lambda, and usually the wavelengths are measured in nanometers. So usually the wavelengths are measured in nanometers. So this 4.86174 into 10 to the power negative 7 meter can be converted into nanometer just by shifting these two digits to the right. So this can also be written as lambda is equals to 486.174 into 10 to the power of negative 9 meter, and 10 to the power negative 9 it's called as nano, right? So that's what I can represent here as, sorry, 10 to the power of negative 9 it's called as a nano. 1 into 10 to the power negative 9, that's 10 to the power negative 9, its value is it's said to be a nano. So this will be written as, so wavelength here is going to be 486.174 nanometer. So this is the wavelength. So by referring to this wavelength, we have to check out what is the spectrum of the hydrogen element which has been provided. From that one we can predict. So let me show you the spectrum of the hydrogen element. So when we are talking about the spectrums, the spectrums are represented in two ways. One is called the continuous spectrum. This kind of spectrum, will be emerged by the white light. When a white light is passes through a prism, when it comes out, so different colors are emitted. So as the different color light has the different wavelength, because of that one, so we will be getting the spectrum of like this. So white light, let's say this is an experimental white light. If it is this is the white light, and when it goes through and passes out of the prism, so the different color of light will be emitted. That is what we say the Wibjer and all. And this type of spectrum, the spectrum represented for the white light is called the continuous spectrum. But actually the spectrum for the elements, so the hydrogen element, so how the hydrogen element spectrums are generated? A hydrogen gas is filled in a tube, and through that tube electricity, a current is passed, and because of that current, electron in the hydrogen atom gains the energy, and they jumps from the lower energy level to the higher energy level. As they jumps to the higher energy level, while coming back from the higher energy level to the lower energy level, they emits the light, and that's what we say, the emit the light in the form of a photon, and that's what we say. And the color of the light will be depends on their wavelength. So for example, if the wavelength of that light which has been emitting, it's going to be 397 nanometer, because wavelengths are measured in terms of nanometer here, you're going to get it as the purple color. In our case, we got the wavelength here as 486 nanometer, and the 486 nanometer wavelength here is going to be a blue color. So this is what the blue color light. So this is what I'm going to choose the option here. If the wavelength of the emitted electron or the photon is going to be 656 nanometer, then the color which is emitted is going to be the red color. So this is how we decide based on the spectrum of the hydrogen element. And whenever the spectrums are represented in this form, these type of spectrums are called line spectrum. Line spectrum. So the first one what we represented was the continuous spectrum, and this is the line spectrum, and this is the spectrum for the different elements. Let me tell you, in the periodic table, according to the chemistry, we know that there are almost 108 elements, and how those element has been categorized depending upon the color what they emits. Different element emits the different color, so based on then it has been classified and the name has been given to us. So far we are just looking for the questions to find what is the color of the light. So the color of the light what I supposed to choose here is going to be blue color, and the option which are given to us is orange, yellow, blue. So I'll be going with the option C. This is the color of the light which is emitted with the frequency here is going to be blue. That is the answer to question number 17.